Good morning to everyone. We are in the we are dealing with the course on advanced hydraulics, and in the fourth module we are studying the hydraulic jumps. In the last class we have discussed on the use of hydraulic jumps as an energy dissipator. We also introduced to you the concept of stilling basins, how the jump positions are varied for a fixed tailwater condition, how the fluctuating tailwater conditions can also influence the jump positions, what are the different types of jumps that are normally used for energy dissipation, and also we have briefly introduced to you jumps in sloping channels. That portion we have to continue today, means we have just introduced to you how the jump can occur in the sloping channels. So, in the jumps in the sloping channels, if you recall them, it is formed when a supercritical flow from steep channel merges with horizontal channel, or in the or it can be a mild channel also. The momentum transport equation was given for a control volume, right? If you recall them, the control volume was specified and momentum transport equation was given in the following form. So, you know that the net or whatever, this is the material derivative of the momentum, this left hand term of this equation. So, it is the material derivative or time derivative of change of momentum. So, the rate of change of momentum is the net force in the system, and this you know it is the net outflux of momentum, and this is the change in momentum stored inside the control volume. So, as it is a steady state condition, this portion we are neglecting and considering it as 0, if you recall them, isn't it? So, and this is the net force. So, this portion will give you the net force, that also we have studied. Now, before continuing with this portion, let me give you briefly the solutions of the last day's quiz. It was due to the time constraint, the solutions were not mentioned in that lecture. So, I will just briefly describe it. So, the first question asked in the quiz was, based on the fixed tailwater depth, enumerate the different cases of jump positions in a stilling basin. I hope you can easily answer them. If you know that y 2 dash and y 2, the tailwater depth as well as the sequent depth, you have studied that, right. So, based on that, if the tailwater depth and sequent depth are same, if y 2 dash is equal to y 2, then jump will occur in the stilling basin itself. So, this is case 1. So, case 2 we have studied when y 2 dash is less than y 2, that is your tailwater depth is less than your sequent depth, then jump will occur downstream. At the downstream of stilling basin. So, that is it will be pushed further. So, it may not even occur in the stilling basin itself. Case 3 which we would like to enumerate is case where the tailwater depth is greater than the sequent depth of the hydraulic jump, then the jump is forced upstream. There may be even cases where submerged jumps may occur also, right. So, just this is the answer for that question. Next question we had asked was, why the weight of water in hydraulic jump is neglected in horizontal channels while it is significant in sloping channels. So, you just need to draw the figure horizontal channel, jump, occurring there just show that in the hydraulic jump the weight of water is acting vertically downwards, the flow is horizontal. So, there is no component of weight in the flow direction, whereas in the sloping channel the same jump occurs, and if you take the volume, you will see that the weight is acting vertically downwards. However, there is a component w sin theta that also contributes to the flow, or it is in the direction of flow. So, therefore, you cannot neglect weight of water in hydraulic jumps in sloping channels. So, you have seen the solutions of the last day's quiz. Now, coming back into the hydraulic jumps in sloping channels. So, as we can see it from a side section, the jump, the weight of the water is significant, as you can see it here. I am just describing a control volume given in the red color here. So, that control volume if you take into account. So, the control surfaces, I am just taking the control volume. So, here you have depth d1, here you have depth d2, right, and there is weight of water acting downwards. So, when you applied the momentum transport equation in this control volume, you have seen that the portion across the control surfaces V rho V dot n dA, this was nothing but equal to rho into V 1 bar okay, I can just show it exactly, V 1 bar into minus V 1 bar A 1, then plus rho V 2 bar. So, bar means the average velocity of that section is being taken, V 2 bar A 2. This was this you are quite clear. So, from this thing, as the conditions are steady, we suggested V 1 bar A 1 is equal to V 2 bar A 2. So, you can directly substitute these quantities also if you require. So, I can write the net outflux of momentum through the control surfaces is nothing but rho into discharge into V 2 minus V 1 bar. The net rate of change of momentum is equal to the rate of change of momentum is equal to the net force in the control volume. For example, in the direction of flow. So, in the direction of flow, let me consider the net force as sigma Fx. So, therefore, sigma Fx, it consists of, just look into the picture here, it will consist of pressure force that will act on this control volume, pressure force that will act on that control surface there, pressure force that acts on the control surface there here. As this is a predominantly one dimensional case, we are not considering any flow perpendicular to the screen, whichever you are seeing here, you are considering only a unit width in the perpendicular direction to the screen here, and the top and bottom boundaries, they are not allowing any flow passing through them. So, the pressure forces will be on this location and as well as on this location. So, I can give this as F P 1 then Fp2, you have component of weight in this direction. So, the net force will be Fp1 minus Fp2 plus W sin theta. Actually, theoretically speaking, frictional force should also have been there, but you are neglecting frictional force. You are neglecting frictional force for all types of hydraulic jump. So, we can now suggest sigma Fx is equal to Fp1 minus Fp2 plus W sin theta is equal to rho times discharge into V2 minus V1. Once you get this relationship, now you can easily identify what are the pressure forces Fp1, Fp2 and what is the force due to the weight, that also can be taken. So, what is Fp1? Say if you have a depth like this, this is depth d1, the corresponding from this location the depth to the bed will be actually vertical depth will be y1, right, and it is on this direction the pressure forces will be acting. So, we have Fp1, the pressure force will be, or the pressure distribution can be given as such, and this force is evaluated as Fp1 is equal to half times rho g d1 cos theta into d1. So, this is nothing but equal to half times rho g d1 squared cos theta. Similarly, in the upstream downstream condition where the slanting depth is d2 and vertical depth can be considered as y2, you know the relationship d1 is equal to y1 cos theta, d2 is equal to y2 cos theta. It is simple trigonometrical this relationship. Pressure force on this boundary, I can just give it as the pressure distribution like this. There also Fp2 is equal to rho g d2 square cos theta. What is the weight of water? How do you take into account weight of water? If the jump was in a horizontal channel, and if the profile, hydraulic jump profile is a straight line like this, if it is a straight line like this, then it would have been much easier for you to evaluate the weight of water, right. In such situation, W is nothing but equal to here, this is y1, this is y2, and say this is the length of the jump L. So, W is equal to half times, you are taking per unit width of the channel or stream, you are taking the conditions. So, the weight per unit width of the channel or stream, this can be given as half times rho g L into y1 plus y2. So, this is the theoretically possible weight of water for such a ideal situation where the flow profile is a straight line. Now, in the sloping channel, we already have a slope. Not only that, the jump is not having a straight, means the hydraulic jump profile is not a straight line. So, taking into account all these factors, we can approximate W is approximated by a relation such a way that W is equal to half times rho g L into d1 plus d2, same as the above case, but this will also be multiplied by a factor k. So, k a factor, it is greater than 1, usually greater than 1, and this factor is being taken so as to accounting for slope as well as profile variation. Okay. So, we are taking a factor like this. So, we can now write, say W is equal to half times rho g k times L into d1 plus d2. So, you also have F P1 is equal to half times rho g d1 squared cos theta, F P2 is equal to half times rho g d2 squared cos theta. Therefore, going back into the equation, this particular equation, we will be writing it again. Rho q V1 bar minus V2 bar is nothing but equal to half times rho g d1 squared minus d2 squared cos theta plus KL d1 plus d2 and W sin theta is the component, right. So, KL d1 plus d2 sin theta. So, we can eliminate rho from the equation. You will see q times V1 bar minus V2 bar is equal to g by 2 d1 squared minus d2 squared cos theta plus KL sin theta d1 plus d2, like this you can write. So, we have already seen q, it is function of q is nothing but V1 into A1. Now, as we are taking unit width, perpendicular to the screen here, we are taking the unit width, right. So, q is nothing but V1 into D1, this is also equal to V2 into D2. So, what does that mean? You can have easily the relationship V2, therefore, V2 is equal to V1 D1 by D2. Why we are writing it like this? Because the pre-jump depth and the pre-jump conditions are mostly available to you. So, we are determining the post-jump situations, with respect to the pre-jump day. So, therefore, I am writing velocity v 2 is equal to v 1 times d 1 by d 2. You can substitute those quantity in the above equation. You will see that this becomes v 1 bar d 1 into d 1 by d 2 minus v 1 bar is equal to g by 2 d 1 squared minus d 2 squared cos theta plus k L sin theta into d 1 plus d 2. Like this we can rearrange them. You can again work it out. You will see that, say, we know the upstream fluid number. So, upstream fluid number is nothing but v 1 square by g d 1, right. So, the square root the square of the fluid number can be described like this. You can directly substitute this quantity now in the following equation also. So, you will get Fr1 square g times d 1 into d 1 by d 2 into d 1 minus d 2. This is nothing but equal to g by 2 d 1 minus d 2 into d 1 plus d 2 cos theta plus, you can again write it, rearrange the quantities here, k L sin theta d 1 minus d 2 into d 1 plus d 2 by d 1 minus d 2, just for our benefit, so that I can now cancel d 1 minus d 2 everywhere. For that purpose, we have written it like this. So, this equation becomes Fr1 square d 1 times d 1 by d 2 is equal to half of d 1 plus d 2 into cos theta plus k L sin theta by d 1 minus d 2. Like this we can come into derivation there. You can again rearrange the things here, that is d 2 by d 1 into, you are just taking the inverse of the above relationship, you will get the following form: 2 by d 2 by d 1 into d 1 plus d 2 into 1 by cos theta minus k L sin theta by d 2 minus d 1. Here I have just taken it instead of d 1 minus d 2 d 2. Therefore, that negative sign appears in the formulation. You can further proceed with rearranging the terms. So, I can just means we can follow it. Now, at this stage we expect you to work it out further, and as given in Venti-Chow's book, Venti-Chow's open channel hydraulics, the above equation can be simplified and it can be written in the following form. d2 minus d1 whole cube by a quantity g, 2g squared plus 1. Okay, I will just write it in the next page, the simplified form, d2 by d1 whole cube minus 2g squared plus 1 d2 by d1 plus twice g squared is equal to 0, where the quantity g is nothing but equal to the upstream fluid number divided by the square root of cos theta minus KL sin theta d2 minus d1. So, if you can define g in this way and if you incorporate, you can see a third degree polynomial or an equation with respect to d2 by d1, and that can be now easily used. You will see that one solution of this equation, say if I name it as A, one solution of equation A is d2 by d1 is equal to half of root of 1 plus 8 times g squared minus 1. So, if this gets clear, you will see that you will get a depth ratios for the sloping channels, d2 by d1 is equal to in the following form also, right. So, this like this relationship also you will get for the sloping channels, as d1 is equal to y1 cos theta, d2 is equal to y2 cos theta. The above relationship can be changed to vertical depth, y2 minus y1 is equal to half of root of 1 plus 8 g squared minus 1, right. So, you are getting the depth ratios y2 by y1 or d2 by d1. So, this function, that is depth ratios, they are functions of the upstream fluid number and bed slope. See, you have the bed, channel bed like this, and this is theta. So, definitely it is a function of theta, right. So, theta means I can represent it in terms of the bed slope as 0. So, we write this as function of FR1 and theta, either like this function of FR1 theta like this I can write, or I can write function of FR1 and the bed slope as 0, like this also one can write. You can also plot, that is FR1 versus y2 by y1. See, like this different curves you will get for different slopes. Say SR S0 is equal to some magnitude x, S0 is equal to some magnitude y, S0 is equal to some magnitude y2, whatever be some magnitude. So, for different slopes you can plot this thing, and these standard charts are also available. One can easily go through that chart and also get the sequent depth if this for the corresponding slope. That is also quite possible. Next, we will discuss on control of jumps. Hydraulic, as we have studied earlier, hydraulic jumps require some certain controls, so that it will be held within that stilling basin. Otherwise, you have seen how it can be pushed the upstream, or it can be pushed downstream, or it can get washed away. So, there are various provisions of controlling the hydraulic jumps, and the jump, one of the important things is, or one of the most commonly used thing is sills. You can control hydraulic jump by sills. What are the sills? You can use sharp crested weir for controlling the hydraulic jump. You can use the broad crested weir, or you can provide abrupt rise in the bed floor, or you can provide abrupt drop in the bed floor. How it looks? For example, a sharp crested weir, if I draw the channel longitudinal profile of the thing, so you are having a hydraulic jump like this with rollers and all. Then you see that you want to control it within this span. So, you are providing a sharp crested weir here, so that the profile now looks like this. So, this is the pre-jump depth y1, this depth is the sequent depth of y1, and this is the tailwater depth, and the height of this sill, this sharp crested weir sill, is h. Similarly, for a broad crested weir also can be employed for controlling the hydraulic jump in within the specific location. So, if you have a jump, now by providing a sharp crested weir somewhere here, you may see that the flow profile will go like this and it may come up like this. So, again this is tailwater depth y3, this is the pre-jump depth, this is the sequent depth of the jump, and this is the height of the sill. Similarly, so you can just provide rollers, show that it is suggesting hydraulic jump. It is not a gradually provided profile, it is a rapidly varying profile. Similarly, if you can provide abrupt rise of the bed, see the same jump, we can provide abrupt rise. So, it will come like this and it will go continue with those things, the bed will be rise from this location. So, this is y2, y1 and this is y3. So, height of the sill is same h. Similarly, abrupt drop in bed. So, we will see for what all conditions these things are being taken into account, abrupt drop in the bed. So, this is the sequent depth, this is the pre-jump depth. So, we will discuss all those things. So, what is the function of a sill? Because the sill has to ensure proper formation of the jump within that silling basin, and also to control the jump positions under all operating conditions. So, the flow may vary in that in that channel, the flow may vary, the amount of discharge may get varied and all. So, you have to ensure that the jump is occurring in that position, particular position itself. So, for those conditions also the jump control of jumps are required. So, what are the various forces? You can see that the different forces acting on the sill on a jump. So, the forces, it decreases rapidly to a minimum value if the downstream end of the jump is moved upstream to a position approximately over the sill. For example, if I am providing a weir, sharp crested weir, and you see a jump position is like this in this case. So, here what happens is that whatever force is there, suppose if the jump would have been extended further downstream, and if this is moved in this direction, the jump position is, it will be minimum over the sill. So, the jump position, it should end at the sill, top of the sill, then the force exerted on the sill will be minimum. Now, if it goes further upstream, the forces may gradually increase. So, that way one can design the jumps for the, or you can provide proper designs for the control mechanisms. What are the reasons that cause such changes in force? You know that the velocity distribution both in the upstream and the downstream conditions, just in the jump situations, it may not be uniform or it may be quite different due to various rolling effects and all. So, there will be different momentum distribution as well that can cause us different distribution of forces and all. So, you can describe those theory in that way. So, from the experimental it is quite difficult to theoretically explain or quite difficult to theoretically formulate the equations related to control sections and all. So, many experimental studies are done. So, from the experimental data as given in V.T. Chow's book, V.T. Chow's, it is a quite old book on open channel hydraulics, so it is standard book. So, if you refer that book, you will say, for example, in the case of a sharp crested weir or any case, any sill, not only sharp crested weir, broad crested weir or abrupt rise, whatever be. So, there are the following parameters, that is the height of the sill, the pre-jump depth, the sequent depth of the jump and the tail water depth. Following 4 depths are available or following 4 depths are present in such control mechanisms. So, from various experimental studies, it has been observed that the ratio, the following ratio, that is the height of the sill by the pre-jump depth, they have considered it as some function, it is some function of the incoming flow fluid number, that is the fluid number at this incoming section or at the pre-jump depth section, ratio of x by y 2 and ratio of y 3 by y 1. What is capital X here? It is the distance from the toe of the jump to or from the beginning of the jump location to the toe of this sill. Okay. So, this distance is called x. So, like that from the experimental scientists it is been observed, means this particular means it is a ratio h by y 1 is always a function of fluid number x by y 2 and y 3 by y 1. So, once you incorporate these mechanisms, then the design of the sill will be appropriate, or means you can design the cells in a better way. So, usually we use modeling studies, as we told earlier, the theoretical studies or theoretical explanations are quite difficult. So, usually use modeling studies, we can define these for various conditions. We can define for sharp crested weir, for broadly crested weir and all. We can define or we can devise charts for designing purposes. So, modeling studies means dimensionless analysis. You use the various dimensions and all, you can obtain the non-dimensional forms and all. So, usually using those mechanisms and all, one can infer the design mechanisms for sills. For example, control of jump by sharp crested weir. Say if you have sharp crested weir, how do you control the jump? I have the jump here and I am incorporating the sharp crested weir. So, let us consider this as y 1, y 3. I hope you all recall that the hydraulic jump portion which we are studying right now, it is in steady state condition. So, and in this particular case, let us assume that the tailwater depth is not influencing the jump. The tailwater depth is not influencing the jump. Okay. If you give these assumptions and all, so you will see that for y3 say, these mechanisms, that is the tailwater will not influence the jump, it can be suggested only for the following cases, that is when y3 is less than y2 minus 0.75 h. This is also empirically means they have obtained it through their experimental studies. If y3 increases beyond this thing, then it definitely affects the position of the jump and all. So, based on these criteria, we can devise the following charts. You can see them. So, if y3 is not influencing the thing case, then as we suggested h by in the previous slide, h by y1 is equal to, so h by y1 is equal to function of Froude number x by y2, y3 by y1. Now, if y3 is not influencing the hydraulic jump, then we can easily suggest your following this thing is, in this case is h by y1 is some function of Froude number and y2 by y1, because y3 is not influencing the situation. Again, how do you define this situation? Now, y2 we can't say it is exactly measurable, or y1 is the more appropriate term that can be measured, and for designing we want to basically we want to know at what distance from the beginning of the jump should we provide the sill. Okay, so, this x is the important parameter that we need to design, isn't it? So, that way we can now suggest that following relationship, that is we can devise curves h by y1 ratio with respect to the incoming flow Froude number. Following curves, say Froude number, it may be 1, 2, 3, 4, 5, 6 like that. So, we can have various curves for different values of x by y2. Okay. We can have various values for x by y2 as suggested here. So, x by y2 is the relation. So, we have in this case for say the sharp crested Weir, h by y1 is ratio of fr1 and x by y2. So, therefore, this is one particular curve. For another value of x by y2, you have, say let me write this as some numerical value a. Say please note that it is not a variable, it is just some numerical value a. It can be 1, it can be 2, it can be 3, 4. This is for x by y2 is equal to certain quantity, say b, x by y2 is equal to c. So, such design such charts if you can prepare from your experimental or modeling studies and all. Definitely here you should note that a is definitely greater than b, it is greater than c. So, if x by y2 ratio, if it is small, your curve will be h by y1 versus fr1 curve will be looking like this. Now, if it is little bit greater, it will look like that. For higher values of x by y2 ratio, it will be looking like this. So, like this curves you can prepare, and based on that based on the means you can now appropriately suggest what could be the height of the sill given the following criteria and all. Say for a given fluid number, the height, if that fluid number is maintained, you can suggest that if the x by y 2 ratio is A, then the h by y 1 ratio should be following thing. One can easily interpret for designing. So, again I am just redrawing the thing here. You can see that as this is fluid number, this is h by y 1 number, and this is the curve for any particular value of x by y 2 ratio. So, in this case you have say points lying above this particular line of x by y 2, you have points lying below and also on the right of this x by y 2 curve. So, you can have two different situations. What does this infer? So, here points that lie above this particular curve, it suggests that weir is too high in these locations. So, for such ratios the weir height is or the height of the sill sharp crested weir is too high. In this these cases the weir is too low. So, the jump weir is too low. So, the jump may be pushed, downwards. Further downstream the jump will be pushed, or it may get washed away also. In this case the jump will move upwards. So, for the following x by y 2 condition, if you are providing the h by y 1 ratio in the upper cases, so this is what it will happen. That is the meaning of this such curves and all. So, usually for design purpose, the curve meant for x by y 2 is equal to phi ratio, whichever curve is developed, that is generally used for the design purpose. They are generally used. Next we will see control, that is again the control of jump using broad crested weir. So, you have a broad crested weir for the jump. So, you can have different tailwater depth. There is again this is the pre-jump depth, this is the sequent depth of the pre-jump, this is the height of the sill, and here let us assume y 3 as the tailwater depth. So, if for these following conditions, the one criteria or one of the situations, that is how the broad crested weir act as a control, is that one thing you have to remember is that the minimum possible flow or the type of flow that can be possible over the weir, it should be at least critical, right. That is, you are having a subcritical flow here and it will just slow down the energy, that is it will just slow down and it can reach up to the critical flow. That is the requirement. So, using the specific energy theorems and all, you can easily devise what should be the depth of flow over the weir, broad crested weir and all, like that can be devised. Again y 3, so that we do not have influence of tailwater depth on the flow. For that criteria is the thing suggested. So, you know that critical depth over the Weir, this can be given as V by C over the Weir. This is equal to the discharge per unit width by G whole to the power of 1 by 3. This I hope you can require, as we are all taking the rectangular Weir, that is the reason. So, Q is discharge per unit weight. So, applying the conservation specific energy theorem, just say in these particular situations, say maybe in these following sections. So, using the specific energy equation for the two sections, say if this is your broad crested Weir of height h, then this is where the jump is coming now. So, for these two sections, in these two sections we can suggest, say here this is y2. So, between these two sections the energy equation will look like this: y2 plus q squared by 2g y2 squared is equal to. So, here this is y2 minus h, y2 minus h plus q squared by 2g y2 minus h whole square. So, using such specific energy equations, you can now find the relationship of q squared, that is what is the discharge per unit width. So, that you can get it as 2g y2 squared into y2 minus h. You just rearrange the terms, you will get the following relationship, right. Now, we can also see that q is nothing but the velocity at section 1, that is pre-jump depth at the pre-jump condition. So, this is a known value to you, velocity is known to you, y1 is known to you. So, that also you can easily it is available. You also know the fluid number at the pre-jump section, V1 squared by G y1 is the square of the fluid number. So, you can substitute these quantities in this particular equation, fine, and what we will get is that we will get relations of fluid 1 versus h by y1. So, if these plots are given to you, so for different values of fluid number, what is this depth ratio h by y1 for this condition? If it is plotted, you can design the seal appropriately. So, you can give such plots now, say h by y1 for different fluid number, you can plot like this. Now, here you will see that the ratios are only functions of h by y1 and fluid number, or h by y1 is function of only fluid number. We are not taking x by y2 or even y3 by y1 ratios and all. So, that is only for the broad crested Weir. What is the advantage of broad crested Weir? Advantage of broad crested Weir. So, broad crested, they are structurally stable, structural stability and lower cost of construction compared to abrupt rise. So, for these cases you use broad crested Weir. So, that way I was thinking of continuing the other two cases of controls, but however, due to time limit we will continue it in the next class. We will have a quick quiz related to the following topic. So, the first question is, For a hydraulic jump in a sloping channel, a function g was derived, that is g is function of fluid number and theta, if you recall them. So, that is g was given in the following form. Give the expression for depth ratios. Also express the depth ratio if theta is equal to 0. Your second question, what are the sills used to control the hydraulic jumps? What are the different sills you have just, so briefly tell them, no need to describe about them, just give the names. So, the solution for this case are, you have the depth ratios d2 by d1 is equal to half of root of 1 plus 8 g squared minus 1. This is same as the vertical depth ratio y2 by y1 also, right. This is how the depth ratio expression is given to you. So, if theta is equal to 0, then what happens? G is equal to FR1 itself. So, you will get the depth ratio y2 by y1 appropriately. For the next question, what are the sills used to control hydraulic jumps? So, you know the solution for that, broad sharp crested, broad crested, then abrupt rise, abrupt rise in the bed, abrupt lowering of the bed. So, these are the answers for the second question.